is Cade. Cade is he's at UV here. He's probably just running a little late. I think he had a class that ended at 2:30, but he should know. Do we like the lights on or off?
Off's good. Makes the projector light less harmful to my eyes.
Off is good.
Yeah. I know, counterintuitively.
Okay. Yeah. It's movie theater. Okay. Yeah, we're ready to go.
Okay. Well, my name is Job McKee. I'm going to be talking to you guys about what I've been doing with Dr. Fennell for about the last year. And we've basically been modeling condensed phase alcohol molecules and trying to make them behave more realistically by altering the polar-nonpolar balance of individual molecules. And we'll get into exactly what methods we've used. We'll first look at the motivation behind this research and what we hope to accomplish. Then we'll talk about how we have done what we've done so far. And then we'll get into the interesting part, the results. So I'll try to breeze through the beginning stuff since you all are probably more knowledgeable than the average person at a conference about molecular dynamics. So first of all, some motivation. We want to build better models, but why is this? Aren't the ones we have good enough? Well, it's been proven and demonstrated time and time again that at this point, virtual labs, like simulations, can compete with real labs as far as discoveries and determining properties of compounds. So they're absolutely useful. And they're also, in some cases, more versatile. Like you can do things in simulations that you just literally can't do in real labs. And this comes with the expense or the downside of expense, but this disadvantage becomes less severe as you scale up. So by using the supercomputer, we're not paying quite as much for electricity as we would per discovery. You could think of it as that way.
Someone's bad.
Yeah, we're very privileged. So my research uses the general Amber force field model. That was our initial starting point. And from there, we tried to improve that. This is a pretty good starting point for simulating many properties at once, which is desirable for things like biochemical drug discoveries, applications, and the GAF model is also used in conjunction or in alternation with these other models. But we are just using the GAF in this research. So a little bit about the background of alcohols and water in particular. Water bucks all the normal trends that you might expect from structural analysis of the molecules. It has very different boiling point and density and heat capacity than all the other things that are kind of structurally similar. All that to say, the work that has gone into simulating water with high fidelity is not really applicable to other things, even very simple things. So we're kind of starting, not quite the Stone Age, but not where the simulations of water are at. So this is a bit about how the GAF model works under the hood. It effectively treats pairs of atoms like they're balls and springs instead of like atoms with electron clouds. And it controls these interactions between the two balls by sigma and epsilon values, which basically represent the distance that the pair prefer to be at relative to one another. If you alter sigma, that distance can change. And epsilon, the well depth, is we call it stickiness, makes it easy to think of like that, of the molecules. And so in my research, we alter these two parameters for this type of simulation. And we alter them independently per atom type. I don't know if you can see this. It is not quite as big as I expected, but say, for instance, we would just be altering the sigma and or epsilon for one part of the atom, not the whole thing. So that's the main conceit of the research. And we use alcohols because of their sort of additive structure. Whenever you increase the chain length, the hydroxyl portion does not change. So that's kind of like changing one variable at a time. So now on to scaling the nonpolar polar portions, how this actually functions on a execution level and why it was proposed. Alcohols, these three properties in particular, are well validated experimentally. So they give us something to sort of, they make a good frame of reference for whatever changes we make. We can try to get back to these points and then know that we still are working with effectively the same molecule. So say for instance, we want to alter a sigma for the nonpolar portion. For methanol, it just amounts to the 1 carbon. So we'll increase the sigma for that part. And obviously that throws off the experiment properties and simulation, and we're suddenly no longer working with methanol. It's something far different and more caricature-like. So maybe intuitively we can fix this by scaling the opposite part of the molecule until our experimental values once again align with what we would want them to. And going back to the original state, we do the same thing for epsilon. It's not as easy to show in a picture, but the stickiness, if we alter that for the nonpolar portion, then by altering the stickiness for the polar portion in some other way, we can once again achieve these 3 properties. So how can we actually optimize these 3 properties? How does the process work? Whenever we alter the nonpolar portion, how does the polar portion get fixed to give us parameters that we want? We used an existing in-house program, so it was minimally taxing to my programming skills, from a 2014 paper Dr. Fennell co-authored with Dr. Mobley. And it basically relies on supplying an initial molecule, and you supply allowed parameters for the properties you're searching for. And so it calculates the density for the system, and then if it's within your tolerance, it calculates the permittivity for the system. And if those are within parameters, within the allowed tolerance rather, then it calculates a 3rd property, the enthalpy of vaporization. Now let's say at this point, for argument's sake, that the enthalpy of vaporization was not within the tolerance point, then it would just fail. And so it would start over. And computers are good at loops, so it'll just loop and loop and loop until eventually it does find some scaling for the polar portion that successfully reproduces those 3 properties. And so at this point, we stuck in a tweaked molecule, and we got out one that has retained those 3 properties relative to what we started with. And we did this several times, several hundred times, in fact, for all reasonable scalings of sigma and epsilon. We just altered them progressively and filled in all possible combinations of those scalings to give us a 13 by 13 grid. I just made this bigger grid so you could get an idea of what's happening, of methanol molecules. So ideally, whenever we finish optimizing, we would have a 13 by 13 grid of perfectly identical methanol molecules, at least with those 3 properties being identical. And so the first results, this was sort of round 1 of the process, was building the systems. So from our initial GAF model, we built a grid of scaled molecules, and these were the results. We ended up, the green ones represent successfully optimized models while the red ones failed. And it's kind of a clear pattern of success and failure. So the green ones are perfectly viable and all virtually identical for those 3 properties. They're within 5% of those 3 properties mentioned. But what's up with, oh right, so we have a 13 by 10 grid of actually useful results. But let's stop down and talk about the sort of the cliff edge where they're just running to their death, we joked. It is a sort of a simulation shortcoming, the way that the hydroxyl group is simulated. The hydrogen of the hydroxyl group is within the oxygen's cloud. And so by scaling the sigma for the nonpolar carbon and then telling the program to scale the polar portion, it had to shrink the polar portion so far that it de-shielded the hydrogen from the hydroxyl group, which then the hydrogen could interact with other molecules in the system, and things went very bad very quickly, and irreparable damage to system stability occurred. So we just sort of left those for dead. But We would expect to find this in any direction that we go of scaling these variables. It's just a matter of that we found it first at a arbitrary point. We're not particularly interested in the extremes. We kind of would intuitively know that that won't be very realistic for most physical properties that we care about simulating. So, but what's to say of the 130, which are better than another? They all have the same three properties in common. Well, we can introduce a fourth experimental property, diffusion or diffusivity. And this is another good parameter to monitor because it's well studied for alcohols in particular. And so just a little bit about the trends of diffusivity. It's higher for smaller molecules. And as you increase the alcohol chain, the diffusivity lowers because the molecule is more bulky and can't volatilize as well. So that's the general trend. And onto this plot, we can ideally plot our diffusion for each of those 130 successfully optimized systems. And there would be 130 dots in the methanol effectively, and we would be interested in ones that best replicated the diffusivity as well for methanol. Now, it sort of branches here, and I haven't talked about it before now, but we extend this system epsilon sigma scaling to each of these other molecules. So we have 130 different permutations for the ethanol, and then propanol and butanol. So this gives hundreds of more dots. And we eventually are left with like 520 different systems, differently scaled for sigma and epsilon. Just to briefly talk about how we calculate these values for each individual system. Just a mathematical trick called linear regression, where we graph the diffusion per system. Oh, sorry, I left this out too. For each of those dots, each dot really represents 5 or 6 individual systems where we have the box size changing as well. So that is just purely to give us more statistical methods to work with. And by altering the box size, then we can plot the diffusion for the varying box size and find where the y-intercept is and say that that is the diffusion for those scalings for an infinite sized box. So that's how we get the final plot data that we are plotting. And if we connect the same sigma and epsilon scaling across systems, then we can get these trends and observe how they vary in relation to the green experimental data trend. Right, so each trend line represents a specific sigma epsilon scaling, a unique one. Okay, now the results from this part. This is kind of the finale, so prepare yourselves. There's a lot of numbers. Oh no, I'm sorry, not yet. Kind of oversold it. So this is just some actual results from what I've been describing. This is the diffusion for experimental data, the trend.
That's the experimental data?
Yep. Those should be experimentally determined, not for me, like literature results.
Yeah. Do they have errors associated with
Yes, that is a numerical method that I neglected to address. That's a good point. Thank you. But there are the 130 systems for each model.
Again, just so each of those dots represents a system that you ran different box sizes on and fit a line to and got the y-intercept.
That's correct.
And so each of those dots actually has an error associated with it as well.
Yes. It's very preliminary data. There's a lot of null data points, but...
Well, I'm not worried about the null data point. That certainly seems like a concern, but I guess my question is, but there's very clear spread even of these dots, but each dot has an error bar that isn't currently included in the plot.
Right, yep.
Do you have any idea of the size of that error? Would it be important to include?
Yeah, we're still struggling to address the signal to noise ratio for each system, and we've done that in a few different ways. One was the box size. We increased it from what we initially thought would be adequate. So we're using 6 system sizes now instead of just 5. We're also running the simulations for longer to try and increase that ratio.
Well, so, I mean, do you have a concept of what the magnitude of the error is for any one of those points?
It-
From the linear fit that led to those points?
Right. Yeah, it is extremely variable. Like you can see these are kind of clumped above, whereas the methanol is pretty well centered.
No,
But-
okay.
In some cases, the error is like above 100%, so that the slope is the wrong way for the diffusion.
Oh. Okay, I see. You mean if you, but I get, what I'm asking is, each one of those individual circles that represents your data.
Yeah.
Like that highest point at 2, right?
Mhm.
That is coming from a fit of different box size systems, and you get the intercept.
Correct.
Those data points that you fit a line to probably don't fit a line perfectly, for example.
Sure. Hmm.
And so when you do linear regression or least squares or whatever that you're doing to fit that, you can get an error estimate of the parameters of the fit. The parameters of your fit will be the slope and the intercept of the line.
Mhm.
And that error will represent essentially how confident you can be in that value based on the scatter away from a fit line
Right.
of
Mhm.
your data. So, I mean, you could just, most linear regression algorithms will just spit it out for you. You have to ask it for it.
Hmm?
Oh, so
But he isn't plotting.
he's not plugging.
He's not plotting it, we're not factoring in that spread.
Yeah, so that, I understand
But
that.
he has that value.
But do you have any, do you have any concept of the magnitude of that value?
Relative to what it should be, or
Just
absolute?
what is, for any given point, I mean, maybe it's variable, but I assume it's not hugely variable, probably. Because my gut would tell me you don't need it, as in, because because the noise in each is so large, the spread of your systems is so large that you don't really need to include the small error associated with each system. That would be what my gut would tell me, but I don't actually know what the magnitude of that error is.
Letting Joe answer this, do you remember what the spreads were on the intercepts from the regression?
Not particular numbers. I know that some were very extreme, but those were obviously null
Well, I think-
edge cases.
You're remembering the R-square value in the fit on there, I think, when you're talking about the very extreme one. But we didn't really pay too much attention to it on there, but it's around 0.2 in at least these units for the diffusion coefficient. So on this scale, that was about the worst one that I saw from the
Yeah,
ones
so-
that you were showing.
Okay.
So
0.2 would have some effect on the estimate of the error in each individual methanol, whatever, but it won't have a huge one. What has a huge, bigger one is the spread
right,
that we're seeing
exactly.
here.
So the spread that you see here matters a whole lot
Yeah, that's
than
what
the
I
area
was
that you're
trying to
shooting
get.
for right there. So yes, it's a great question and really thinking about what matters for these points right here, and can you trust that point to be right there? Oh, I need to get that exactly at that point. Well, you have a bit of a spread around there. You don't have complete certainty
Sure.
for the experimentally comparable diffusion coefficient for ethanol with those sigma and epsilon scalings, but
But just considering, it was a very undergrad, I would say, question. Undergrad question, what is the error that goes into your final values that you're estimating? And if, for example, you just take the average of those points there,
Mhm.
and the standard deviation or standard error of those points to represent the error, you are ignoring the error in your intercepts. Is that reasonable to do or not reasonable to do?
I wouldn't say that was ever my plan. It sort of
No,
got swept under the rug.
Yeah, but my point is that just making sure you understand that that's what you're doing, and then, if you told me the error is 0.1 or 0.2 of these units, and thus it's going to be a minor contribution to the overall error estimate because of the large spread in this data, that would be a satisfactory answer
Mhm.
to my question.
Right. I could see that.
So that's all.
Okay, thank you. So this is each of the relative system diffusions relative to the experimental data. And if, as before, we plot a line between each identical sigma epsilon scaling, it's pretty ugly. And there's a lot of noise, as I mentioned. This is more the trend we would hope to see, where gradual changes to sigma and epsilon reliably alter the system properties. But we're still addressing many problems in many of those systems. I've not tallied what the spread is, but you can see it's probably below 50% are sensible to any degree. But we're not really interested in the extremes, like I said before. We're interested in ones that best replicate diffusivity data from experiment. So if we restrict our plotting to, say, ones that fall within 20% of any one of the models at any point, then we're left with many fewer and more manageable systems. Another thing to mention is the GAF, the original GAF system. How well does it represent diffusivity? Well, it turns out that most of these systems are better than the GAF diffusivity. And again, I might have glossed over that initially, how the GAF molecules are chronically underpolarized, and it has this effect of lowering diffusion artificially from what it should be. So each one of these systems apparently produces more accurate diffusions for these systems than the GAF original model. And these are some of the sigma and epsilon scaling values that result in these lines. You can kind of see that sigma prefers to be scaled larger, while epsilon kind of goes up and down. This is the part that I was imagining earlier, warning you about. A lot of numbers, so don't panic. This is sort of how we refine the data further. And these are the relative error in each of those vertical plots relative to experiment, how far off it was. And these are just for reference, the sigma epsilon scalings they correlate with. And this, in effect, is the score of each model. And a lower score is better, indicates more valid diffusion results. So the highest ranked model is when we scaled sigma and epsilon by 1.04 and 1.08, 104 and 8% respectively. And those are the difference in error between experiment and each system. And that is ranked higher than this one because, for example, in the very bottom left, you see it simulated methanol with a pretty high disparity between the diffusion it should be and what it actually was. So it has a resulting lower score. But what's up with these that aren't green? Well, whenever we refine our criteria further and say that we want to weight the error, rather the importance of each error of each system, because where we eventually want to take this application is to larger molecules. Not any molecule is as small as methanol. So if it's really good at simulating methanol, it won't really get us much elsewhere. So we don't really care as much. Whereas if it's really good at simulating butanol or something larger, then we care more about those scalings. They show more potential promise. And for this reason, this model, which simulated methanol decently and butanol very well, gains a higher score than it otherwise would have. And in the same way, this one, which was one of the worst for just a traditional root mean squared error treatment, simulates butanol extremely well and methanol not so well. And so it actually rises to the second best model, potentially. Yes.
What are you weighting them
by? By their, we divided their error by the experimental diffusivity for that alcohol.
But what? So you're, in order to get methanol downweighted and butanol upweighted.
Yeah.
You divided it by the experimental diffusivity. I don't understand.
think the thing you can think about here, I'll step in on this, since we just did this week and we're just rank sorting these. So the absolute diffusion value that you have for methanol, for example, is 2.5 or something experimentally, right?
Yes.
And then butanol, it's like 0.6 or
Mhm.
0.5
Oh, I
experimentally.
see.
So if you divide by effectively the absolute, the magnitude of the diffusion value for each one of those, you're going to divide by 2 on methanol and you'll divide by 0.6 on butanol. So then this is effectively going to amplify the weight
So
of
it's a
butanol. So it's sort of an absolute,
it's a root mean percent error or something like that.
right, well, so it's a weighted root mean squared error. So each one of those alcohols is, you're figuring out a square error for each one of the alcohols, and that's what he's showing right here. And then he takes the summation of those, and they're either the straight sum where the weightings are 1, or you have the weightings based upon the, I guess, reciprocal diffusion coefficient of that particular experimental value, that particular molecule. And then you do the sum of those and square root of that.
The assumption being that the larger the value, the larger the diffusivity value, potentially the larger the error.
Right, exactly. That was the motivation on choosing the weighted RMSE, weighted RMSE there. Because, like,
But
if you look at an error on methanol, it's.
But you're already dividing by, right? Because you do the error is the difference between the two divided by.
So you take the square of the difference between the experiment and your measured value. So then.
Oh, you don't divide by the.
We aren't dividing by the magnitude of that there to normalize. And that's effectively what is happening.
Sort of.
Weighted.
Because what I was saying is do a mean squared percent error.
Yeah, that's, we could go that way too. Root mean square, so why would we use root mean square error as opposed to like mean absolute error or mean sign error, Joe? So here's a question for you.
Good
I think
question.
we talk a little bit about root mean square error and why we're choosing that as opposed to just average error or like mean sign error. So what's special about root mean square error?
I hate to say it, but I don't
You don't
remember
remember.
talking about it.
So RMSE, it basically penalizes outliers more. I think this is what
Right,
I mentioned
okay.
to you to
Yep.
some degree, because you're squaring essentially that difference
Yes.
there. So then if you have a large difference for any one of these particular values, then you're squaring it. So then it's like, oh, it's even worse right there. And then you do the summation in there, and then you take the square root after the summation.
Mm.
And it basically has a tendency of, if you have an outlier on the bunch, then it just hits it with a bigger penalty. So then it throws away like totally unrealistic models a little bit more easily than some other errors if you were rank scoring them by error. So, but in practice, like these models, it looks like the ones you've chosen are already sort of reasonable anyway. So we could have used a different error if we wanted to.
Sure.
I have 2 questions, but I can wait till you're done if you want.
I think there's like one more slide. Just,
Doesn't have to.
nope, that is all I have. So please, fire away.
Okay, and it's not about this slide.
Oh.
Specifically, but you can leave it here if you want to. So my first question. In methanol, you're scaling, you scale sigma or epsilon for the polar and non-polar, where the non-polar is the carbon component. In butanol and any of the other ones, you have more than one carbon.
Right. We are only scaling the terminal one.
Only scaling terminal one. Not quite.
So so what you've determined, effectively what you're doing, Joe, here, is you're scanning over all the methanols. You basically scale sigma and epsilon by percentage on the methanol atoms. And these are the methyl group of the methanol atoms that are scaled. We don't even, we start scaling, you don't care about the oxygen because the compute loop that he had.
Yeah, fine, but
Optimizes the
it gets-
hydroxyl.
but it gets scaled somehow.
It gets scaled to try to keep the properties right, but
Yeah.
really, like his 130 or 169 models that he had, those ones are all different scaling combinations for the methyl group. Now, you've determined that for carbon and hydrogen's also scale too on those when that happens. So then when you go to butanol, for example, so we actually scale all of the carbon atoms with that same scaling. So if they had to inflate a little bit, like inflate 5%, for instance, then the terminal methyl is inflated by 5%. The methyls that are along the chain are also inflated. Methylines, right? So we're also inflated by 5%.
So that brings up the question I'm trying, or one of the questions I'm trying to get to. Does that make sense chemically? Would you expect, why would you, should the scaling of each of those be the same? Should the size of each of those atoms be the same?
Well, they're hybridized differently, so than the terminal one.
No, they're all sp3. I mean, they're all tetrahedral, right? You don't have double bonds.
Sorry, yeah, no, that's not the right word. I am not sure.
Well, I mean, it's not an easy question to answer. I mean, what I can tell you is certainly in other force fields, you have carbons are sometimes specified. They're certainly specified by their hybridization, but they're often also specified by their substituents. So a methylene might be scaled differently than a methyl carbon. It might be scaled differently than a carbon connected to a polar group, for example.
Just not the force.
In some force fields, this is true. So certainly, if you have a polar substituent, you could imagine physical arguments to have a different size carbon than if you're not.
Sure.
Because you have different draw of electrons away from the nucleus.
Yep.
So, I mean, it's just something to consider when discussing your model is that you could make it more complicated. For example, you could think about the scalings of different scalings for different carbons. And does that make sense? Is there a reason to do that? I would say yes. There potentially are reasons to do that. Will that improve things? I have absolutely no idea. But physically, I could understand an argument. I could buy an argument to have different scalings and potentially different epsilons on the different carbons. But it's certainly something you should absolutely know what it is that you are doing in your particular thing. But and then the somewhat related question is, why would you expect then, or a similar question would be, why would you expect the scalings to have to be the same in methanol, ethanol, and all of the propanol and butanol?
I don't think we're necessarily expecting them to behave identically. We plan to use these same scalings for things as diverse as diols and ring branch structures, and see how they behave, and see if these scalings have any value, just based on an arbitrary application to a wide variety of molecules.
Because again, for similar arguments I just gave, I wouldn't necessarily expect the scalings to be the same across the board. So when you showed your plot of your crazy string plot, I was like, well, I just picked always pick the scaling that's closest, that yields the best diffusivity for the given system. Now your scalings will all be then different, which, depending on what you're trying to do, is, if, for example, what you're trying to do is then build bigger systems out of these scalings, well, it no longer becomes useful because you have to always run this set of simulations for any system you're choosing, and that becomes cumbersome and annoying. And presumably what you're trying to do here is build up a more general force field. Okay, that's enough of that. A different question: how did you calculate not the diffusivity, I understood you plot you calculate this diffusion for each box size and then you plot that. How are you calculating the diffusion for each box size?
Asking GROMACS for it.
Uh-huh. Okay. What does it represent? What are the units?
Debye. It represents the propensity of a molecule to migrate through space.
Yeah. So how might you think of calculating
As a velocity.
that? Sure.
So it means for displacement maybe.
Yeah, of either of those, there are two different approaches. Einstein and the green Kubo, or whatever the hell it's called. You can either look at the velocity or relation function or the mean squared displacement. But yeah, I mean, my point being that you have to look at how things are moving, and it has a time dependence, right? Now, this is, it's just an undergrad thing, so fair enough. But if you were a grad student in my group telling me that you calculate it from a GROMACS thing, would not go down well. Just, but undergrads. But
Well, Thanks for your understanding.
yeah, okay, good, thanks.
Okay, well, any more questions?
All right, good deal. Thanks, Joe.
Yeah,